Beneath the vast, uncharted skies of the ancient world, civilizations gazed upward and saw not just scattered stars, but a celestial blueprint. Without satellites, calculators, or even the basic tools we take for granted, they mapped the heavens with astonishing accuracy, predicted cosmic events centuries in advance, and built monuments that aligned perfectly with the movements of the sun, moon, and planets. How did they do it? Were they simply lucky, or did they possess a profound understanding of astronomy that we've underestimated? This isn't just a question about the past, it's a mystery that challenges our very perception of human ingenuity. Take a moment to picture the Great Pyramid of Giza, its sides perfectly aligned with the cardinal directions, or the intricate Mayan calendar, which tracked planetary cycles down to the minute. These aren't random feats, they're the work of cultures that studied the night sky with a precision that rivals modern astronomy. And here's the startling part, some of their discoveries still stump scientists today. How could the Babylonians calculate the orbit of Jupiter without telescopes? Why did ancient cultures across the globe, separated by oceans and millennia, build structures that mirror the same celestial patterns? The answers might rewrite what we thought we knew about history. This journey isn't just about uncovering lost knowledge, it's about rediscovering the brilliance of our ancestors. From the star charts of the Dogon people to the eclipse predictions of Stonehenge, we'll piece together a puzzle that spans continents and centuries. Along the way, you'll see how modern researchers are finally beginning to decode these ancient secrets, and why some believe these civilizations might have known more about the cosmos than we've ever realized. So settle in, because by the end of this exploration, you might never look at the night sky or human history the same way again. The stars have stories to tell, and they've been waiting for us to listen. One of the most astonishing examples of ancient astronomical mastery comes from the Maya, whose calculations of the solar year were accurate to within just 32 minutes, a margin of error smaller than what many modern calendars achieve. Their Dresden Codex, a bark paper book filled with intricate glyphs, contains detailed Venus tables that track the planet's cycles with near-perfect precision, predicting its appearances centuries into the future. How did they accomplish this without telescopes or advanced mathematics? The answer lies in generations of meticulous observation. Mayan priests meticulously recorded celestial movements, spotting patterns invisible to the casual observer. Over time, they refined their calculations, creating a system so precise it rivals our own. But the Maya weren't alone in their celestial expertise. Halfway across the world, the builders of the Great Pyramid of Giza aligned its massive limestone blocks to true north with an error of just 3/60ths of a degree. To put that in perspective, even with today's technology, achieving such precision would be a remarkable feat. Some researchers suggest the Egyptians used the stars to guide their work, possibly tracking the simultaneous transit of two bright stars around the pole. Others argue they may have employed geometric techniques lost to time. Whatever their method, the result is undeniable. A structure that speaks to an almost supernatural understanding of the heavens. Then there's Stonehenge, where the towering stones frame the sunrise on the summer solstice with eerie exactness. Built over thousands of years by different cultures, the monument's alignments suggest a deep, shared knowledge of celestial cycles. The same goes for the Nebra Sky Disk, a 3,600-year-old bronze artifact from Germany depicting the Sun, Moon, and Pleiades star cluster, proof that Bronze Age Europeans mapped the sky in ways we're only beginning to comprehend. What ties these disparate cultures together? A reverence for the cosmos that went beyond mere superstition. Their achievements weren't accidents, they were the products of rigorous study, passed down through generations. Whether it was the Babylonians using clay tablets to predict Jupiter's motion or the Polynesians navigating vast oceans by starlight, these civilizations saw the sky not as a mystery, but as a clock, a calendar, and a guide. And that realization forces us to ask, if they could decode the universe with nothing but patience and ingenuity, what else might they have known that we've yet to rediscover? Celestial alignments in ancient monuments aren't just coincidences, they're deliberate masterpieces of engineering and astronomy. Take the Great Pyramid's air shafts, for instance. These narrow tunnels, once dismissed as ventilation passages, actually point directly to key stars in Orion's belt, a constellation linked to Osiris, the Egyptian god of rebirth. The precision is staggering. The southern shaft aligns with Orion at its highest point in the sky around 2500 BCE, a time many scholars believe the pyramid was constructed. This wasn't random. It was a celestial map in stone designed to guide pharaohs to the afterlife among the stars. But Egypt isn't the only place where architecture mirrors the heavens. Across the globe in Cambodia, Angkor Wat's sprawling temple complex mirrors the Draco constellation. Researchers using advanced software found that the positions of Angkor's major temples match the stars of Draco with an uncanny accuracy, especially as they would have appeared in the sky 10,500 years ago. Why that date? Some speculate it references an even older, lost epoch of astronomical knowledge, preserved in myth and later etched into stone. The builders didn't just replicate the stars, they froze a moment in cosmic time. How did cultures separated by continents and centuries achieve such precision? The answer might lie in a shared, painstaking method: horizon astronomy. By tracking the rising and setting points of stars or the sun against fixed landmarks like mountains or notches in stone, ancient astronomers could map the sky's movements with remarkable consistency. The Inca, for example, carved precise sightlines into their sacred stone at Machu Picchu to mark solstices, while Newgrange in Ireland channels the winter solstice sunrise into its inner chamber like a celestial spotlight. These weren't just rituals, they were acts of celestial engineering, blending spirituality with science. What's even more fascinating is the possibility that these cultures might have used sound or water to refine their alignments. Experiments at sites like Chichen Itza reveal that clapping at the base of El Castillo Pyramid produces echoes mimicking the call of the Quetzal bird, a sacred symbol. Some researchers suggest these acoustic effects could have helped priests calibrate alignments by sound, turning architecture into a kind of ancient tuning fork for the cosmos. Similarly, reflective pools of water might have been used to double-check star positions, creating mirror images of the night sky for verification. The deeper we dig into these monuments, the clearer it becomes. Their builders didn't just observe the stars, they conversed with them. Whether through geometry, acoustics, or sheer patience, they encoded celestial knowledge into stone with a sophistication that still leaves modern scientists in awe. And that raises a tantalizing question. If they could achieve this without lenses or computers, what other secrets might their lost science of the stars still hold? The Babylonians didn't just watch the stars, they transformed the night sky into a mathematical masterpiece. Their clay tablets, pressed with cuneiform script over 3,000 years ago, reveal a level of astronomical sophistication that still astonishes researchers today. Take the MUL, a pin, one of the oldest surviving star catalogues, which meticulously lists over 60 stars and constellations alongside their rising and setting dates. But this wasn't just a simple star map, it was a working manual for predicting celestial events, complete with planetary movements, solstice markers, and even the slow wobble of Earth's axis known as the precession of the equinoxes. How did they achieve such precision without telescopes or modern tools? The secret lay in relentless observation. Babylonian astronomers, often temple priests, spent generations tracking the heavens, noting patterns invisible to the untrained eye. They recorded Venus's cycles with such accuracy that their calculations deviated from modern measurements by mere minutes. They even developed early forms of calculus to predict lunar eclipses, using a system now called zigzag functions to model the moon's varying speed across the sky. These weren't just stargazers, they were the first true mathematical astronomers. Their influence rippled far beyond Mesopotamia. When Greek scholars like Hipparchus and Ptolemy began mapping the cosmos centuries later, they built directly on Babylonian foundations. Hipparchus, often called the father of trigonometry, openly credited Babylonian data for his own star catalogue. Even the zodiac, a cornerstone of Western astrology, traces its roots to Babylonian divisions of the ecliptic. But here's what's truly remarkable. While the Greeks theorized about celestial spheres, the Babylonians focused on raw data, creating a pragmatic, observation-driven science that feels almost modern in its approach. Yet some of their discoveries remain unexplained. The mole, a pin, references a shadowy star near Orion, possibly a now-vanished supernova or a comet lost to time. Other tablets describe Jupiter's motion using geometric principles eerily similar to those rediscovered in 14th century Europe. Did later astronomers inherit more than we've acknowledged? The evidence suggests a chain of knowledge stretching from Mesopotamian clay to Renaissance parchment, whispering secrets across millennia. What's often overlooked is how accessible their methods were. Using little more than water clocks and calibrated rods, Babylonian astronomers could measure angles, track time, and predict eclipses with startling reliability. Their work wasn't locked away in elite institutions. It was woven into agriculture, religion, and daily life, proving that the cosmos belonged to everyone. And that legacy challenges us to reconsider who gets credit for humanity's cosmic breakthroughs. After all, when we look up at the stars today, we're seeing them through eyes first trained by Babylon's patient, brilliant watchers of the sky. High on the walls of the Temple of Denderah, an intricate stone zodiac maps the heavens with stunning precision, not as random decoration, but as a celestial blueprint carved into eternity. This 2,000-year-old masterpiece, known as the Denderah Zodiac, depicts constellations we still recognize today, from Taurus the bull to Leo the lion. But unlike modern star charts, this ancient sky map blends astronomy with mythology, showing the goddess nut swallowing the sun each evening to birth it anew at dawn. Was this just symbolic storytelling, or did it hold deeper astronomical meaning? The answer lies in how the Egyptians merged timekeeping with the cosmos. Long before mechanical clocks, Egypt's star clocks, called decans, divided the night into precise intervals. Priests tracked 36 star groups that rose sequentially, each marking a new hour as they appeared above the horizon. These weren't arbitrary markers. The decans aligned with the Nile's flooding season, linking celestial events to earthly survival. The best-preserved example, the diagonal star clock from the tomb of Pharaoh Seti I, still bears the wear of fingers tracing stars across ivory more than 3,000 years ago. Imagine the patience required to refine such a system over generations, watching the same stars shift slightly each year due to Earth's wobble, a phenomenon they documented centuries before Greek astronomers named it the precession of the equinoxes. Yet the Denderah Zodiac sparks fiercer debate. Some scholars argue its circular form mirrors advanced knowledge of celestial mechanics, possibly even representing a precession cycle spanning 26,000 years. Others see it as purely ritualistic, a snapshot of the sky for religious ceremonies. But one detail challenges the latter view. The zodiac's constellations are offset from their modern positions by exactly the amount expected over 2 millennia of precession. Coincidence or proof? The Egyptians calibrated their sky maps with observational rigor. The temple's ceiling holds another clue, a depiction of the 5 visible planets moving along winding paths, their orbits rendered with a sophistication that echoes Babylonian records. Nearby, a carving shows the sun cradled in a boat, a motif once dismissed as myth. Yet modern simulations reveal the sun's position matches the summer solstice sunrise around the time of construction. Even the temple's orientation aligns with the star Sirius, whose annual rising heralded the Nile's flood. Everywhere you look, symbolism and science intertwine. This duality defines ancient Egyptian astronomy. Their star clocks kept time with uncanny accuracy, yet their temples whispered of cosmic rebirth. Their priests recorded planetary motions like meticulous scientists, then inscribed them beside gods and legends. Perhaps the real revelation isn't whether their knowledge was practical or mystical, but that they saw no boundary between the two. For them, the stars were both clockwork and scripture, a language where mathematics and divinity spoke as one. And that perspective might be the most profound lesson they left us, that understanding the cosmos isn't just about calculation, but about connection. The Maya didn't just track time, they wove it into the fabric of their civilization with a precision that still leaves modern astronomers in awe. At the heart of their cosmic mastery was the long count calendar, a sprawling system that measured time in units stretching millions of years into the past and future. Unlike our Gregorian calendar, which resets every year, the long count operated like an odometer for the cosmos, tallying days since a mythical starting point in August of 3114 BCE. But this wasn't just a theoretical exercise. The Maya used it to predict celestial events with breathtaking accuracy, from solar eclipses to the movements of Venus, all without telescopes or modern mathematics. Their secret, a lifetime of observation encoded in bark paper books called codices. The Dresden Codex, one of the few surviving examples, reads like an astronomer's manual. Its Venus tables track the planet's 584-day cycle with an error of just 2 hours, a feat that would challenge modern computers if attempted without optical aids. Even more astonishing, the Codex corrects for the slight discrepancy between Venus's apparent cycle and the solar year, a refinement that required generations of sky watchers noting tiny deviations and adjusting their calculations accordingly. This wasn't guesswork, it was a scientific process honed over centuries. The Caracol Observatory at Chichen Itza stands as a testament to their dedication. Its narrow windows align precisely with Venus's extreme rising and setting points, while the stairway angles mirror the path of the sun during the equinoxes. But the real marvel lies in the building's imperfections. Unlike rigid modern observatories, Caracol's misaligned upper tower suggests the Maya updated its design as their understanding of celestial mechanics evolved. They didn't just build for their time, they left room for future discovery. What's often overlooked is how deeply astronomy permeated Maya life. Farmers planted crops by the Pleiades' first appearance in the spring. Kings timed wars to coincide with Venus's descent into the underworld, believing the planet's movements mirrored battles among the gods. Even their myth of the hero twins, who outwitted the lords of death, aligns with the sun's journey through the Milky Way during the winter solstice. For the Maya, the cosmos wasn't an abstraction. It was a living, breathing force that shaped everything from harvests to politics. Yet their greatest legacy might be their humility. Despite their precision, The Maya acknowledged the universe's complexity by layering multiple calendars, the sacred Tzolk'in, the solar hub, and the long count, each serving a different purpose but interlocking like gears in a celestial clock. They understood that no single system could capture time's full mystery, and perhaps that's the most profound lesson they left us, that true mastery of the heavens begins not with rigid certainty, but with the wisdom to keep watching, learning, and adapting just as they did under the endless starry sky. Buried within the pages of the Surya Sedanta lies a cosmic revelation that defies its age. A mathematical treat is so precise. It calculates the Earth's diameter within 1% of modern measurements and predicts eclipses down to the minute. Written over 1,500 years ago, this ancient Indian text doesn't just describe the heavens, it deciphers them with equations that wouldn't look out of place in a modern astronomy textbook. How could a civilization without telescopes or advanced instruments achieve such accuracy? The answer might lie in a provocative theory that the Surya Sedanta's knowledge wasn't invented but inherited. The text's opening lines claim divine origin, stating it was revealed by the sun god Surya to an ancient sage. While this might sound like myth, the numbers tell a different story. Its planetary models account for elliptical orbits centuries before Kepler, and its value for the length of a solar year, 365 days, 6 hours, 12 minutes, and 30 seconds, is off by just a few minutes from today's calculations. Even more startling, it describes the node points where eclipses occur using terminology eerily similar to modern astrophysics. These aren't rough estimates, they're the product of meticulous, systematic observation. But here's where the mystery deepens. The Surya Sedanta references an even older text, the Pitamaha Siddhanta, now lost to time. Some scholars suggest this could point to a forgotten epoch of astronomical knowledge, perhaps from the Indus Valley civilization, whose advanced urban planning hints at sophisticated celestial understanding. Others propose a more radical idea, that the text preserves fragments of a global prehistoric science, shared across cultures through trade or migration. After all, the same eclipse prediction methods appear in both Babylonian clay tablets and Mayan codices, separated by oceans but united by precision. The implications are profound. If the Surya Sedanta's models weren't developed independently but passed down, it rewrites the timeline of human discovery. Consider its description of yugas, cosmic cycles spanning millions of years, a concept that mirrors modern astronomy's understanding of galactic rotations. Or its calculation of the moon's distance from Earth, accurate to within a few hundred kilometers. These details suggest a continuity of knowledge, a thread stretching back further than written history. Yet the text's true brilliance lies in its practicality. Unlike theoretical Greek astronomy, the Surya Sedanta was a working tool. Sailors used its star charts to navigate the Indian Ocean. Farmers timed planting seasons by its celestial markers. Temples like Konark's Sun Temple were built as stone observatories, their carvings encoding solstice alignments described in the text. This wasn't just academia, it was science woven into daily life, proving that the cosmos belonged to everyone. As modern researchers decode its pages, one question lingers: how much more did these ancient astronomers know that we've yet to rediscover? The Surya Sedanta doesn't just challenge our assumptions about the past, it invites us to look up with fresh wonder, reminding us that the stars have been whispering their secrets for far longer than we've realized. And perhaps in its age-old equations, we're not just uncovering lost knowledge, but reconnecting with a forgotten way of seeing the universe itself. When we think of ancient Greek astronomy, names like Ptolemy and Hipparchus spring to mind, giants whose work shaped Western science for centuries. But peel back the layers of history and a more complex story emerges. The Greeks didn't work in isolation. Their celestial breakthroughs were built on foundations laid by civilizations far older and often overlooked. Take Hipparchus, the father of trigonometry, who openly credited Babylonian star catalogues for his own calculations. His famous discovery of the precession of the equinoxes, the slow wobble of Earth's axis, relied on data painstakingly recorded by Mesopotamian astronomers over centuries. Without their meticulous observations, his revolutionary insight might never have happened. Ptolemy's Almagest, the cornerstone of medieval astronomy, reveals even deeper depths. His planetary models, long hailed as Greek triumphs, bear striking similarities to Babylonian predictive techniques. The so-called Ptolemaic system borrowed entire mathematical methods from clay tablets centuries older, repackaging them with Greek geometrical flair. Even his star catalogue, once thought original, now appears to be a refined version of Hipparchus's work, which itself drew heavily on Babylonian and Egyptian sources. This isn't to diminish their achievements, but to ask, why has history remembered the synthesizers while forgetting the pioneers? The evidence goes beyond star charts. The Greeks' division of the sky into 12 zodiac signs, a direct inheritance from Babylon, their use of the 60-based number system for angular measurements. Another Mesopotamian gift, even the celestial spheres, often attributed to Eudoxus and Aristotle, find echoes in earlier Egyptian cosmology, where the goddess Nut arched over the earth like a starry vault. The Greeks were brilliant translators, transforming raw data into elegant theories, but the raw data wasn't theirs. Yet there's a twist. Some Greek thinkers didn't just borrow, they obscured. Pythagoras, for instance, famously claimed his discoveries as divine revelations, concealing their Babylonian and Indian origins. Later scholars, eager to celebrate Greek genius, often erased the cross-cultural collaborations that made their work possible. The Library of Alexandria, that great repository of knowledge, didn't just house Greek texts, it collected Egyptian, Persian, and Indian manuscripts, only for their contributions to fade from the narrative. What does this rewriting of history cost us? For one, it obscures the true interconnectedness of human discovery. The Greek synthesis was a marvel, but it wasn't created ex nihilo. It stood on the shoulders of watchers who tracked Venus's cycles with clay and reed, who mapped the sky with nothing but patience and naked eyes. Recognizing these debts doesn't diminish Greek brilliance, it reveals something even more profound, that astronomy, like all science, has always been a collective human endeavor spanning cultures and centuries. And perhaps that's the greatest lesson the stars have to teach us. Buried in the dirt of a German forest for millennia, the Nebra Sky Disk gleams with golden arcs and celestial symbols, a 3,600-year-old bronze masterpiece that rewrote Europe's astronomical history. Discovered by treasure hunters in 1999, this fist-sized disk is more than just metal. It's the oldest known concrete depiction of the cosmos, predating Greek astronomy by 1,000 years. On its surface, a cluster of 7 gold dots unmistakably represents the Pleiades, the famous Seven Sisters star cluster, while a golden crescent moon and full circle sun anchor the design. But what's truly astonishing are the 2 sweeping arcs along its edges, precise markers of the solstices, the points where the sun rises and sets at the extremes of its yearly journey. This wasn't just decoration, it was a functional sky map, a handheld observatory forged in bronze. The disk's purpose sparks fierce debate. Some researchers argue it served as a farming calendar, with the Pleiades position signaling optimal planting and harvest times. In ancient Europe, the cluster's spring disappearance and autumn reappearance aligned with crucial agricultural cycles, knowledge preserved in folklore across cultures. Others see it as a sacred object, its gold symbols capturing the moment when a crescent moon nestled near the Pleiades, an event that would have held deep ritual significance. But the most intriguing theory casts the disk as a navigational tool. The ark's angles match the solar positions needed to calculate latitude, suggesting Bronze Age travelers might have used it to guide long-distance journeys across land and sea. Imagine a weary trader holding it aloft at dusk, aligning the gold curves with the horizon to find his way home. What's often overlooked is the disk's craftsmanship. The bronze came from the Alps, the gold from Cornwall, proof of a vast trade network exchanging not just goods but ideas. The maker didn't just punch holes randomly. The Pleiades spacing mirrors their actual celestial arrangement, and the moon's phase corresponds to specific astronomical events. Even more striking, analysis reveals the disk was modified over centuries. Early versions lacked the solstice arcs, which were added later alongside a sun boat motif, a vessel mythically carrying the sun across the sky. This wasn't a static artifact. It evolved, absorbing new knowledge like a living textbook of the stars. The Nebra Sky Disk forces us to reconsider Bronze Age Europe. These weren't primitive people stumbling in the dark. They were meticulous observers who tracked the heavens, encoded their knowledge in metal, and passed it down generations. In its golden curves, we see the birth of European science, not in scrolls or stone tablets, but in a disk small enough to hold in your hand, yet vast enough to contain the sky. And that's the real wonder, that 3.5 millennia ago, someone looked up, understood, and dared to map the universe. For centuries, Polynesian voyagers accomplished what European sailors with compasses and sextants wouldn't dare attempt, crossing thousands of miles of open Pacific using nothing but the stars, the swell of waves, and the flight patterns of birds. Without maps or instruments, they discovered and settled remote islands from Hawaii to New Zealand, their canoes slicing through ocean currents with pinpoint accuracy. This wasn't luck. It was a science one passed down through chance, stick charts, and generations of apprentices who learned to read the night sky like a road map. At the heart of their mastery was wayfinding, a holistic art blending astronomy with intimate knowledge of nature. Navigators memorized the rising and setting positions of over 200 stars, using them as celestial signposts. But stars alone weren't enough. They watched how ocean swells bent around islands, creating subtle patterns in the water's motion. They tracked the direction of migratory birds, knowing certain species flew toward land at dusk. Even clouds gave clues. Their shape and color often hinted at distant islands lying beyond the horizon. Every element of the natural world became part of an intricate navigation system, refined over centuries of exploration. The real genius lay in their mental maps. Polynesians used stick charts, wooden frames with shells and fibers representing currents and islands, not as physical guides, but as teaching tools to visualize ocean dynamics. These weren't taken on voyages. Instead, navigators internalized the patterns, allowing them to feel their position even when clouds obscured the stars. Oral chants preserved critical knowledge, like the star path from Tahiti to Hawaii, which followed the zenith star Hoculaire Arcturus. A slight misjudgment could mean missing land entirely, yet their accuracy was unparalleled. When modern researchers recreated these voyages using traditional methods, they arrived within miles of their targets after weeks at sea. Perhaps most remarkable was their understanding of ETAC, a conceptual framework that allowed navigators to track progress without fixed reference points. Imagine sailing at night with no landmarks. ETAC worked like a mental GPS. By selecting a distant reference island far off the intended route, navigators could triangulate their position based on the changing angles of stars relative to that invisible marker. This abstract thinking, akin to modern celestial navigation, proved they didn't just memorize routes, they understood the geometry of the ocean. Today, this knowledge isn't just history, it's a living tradition. The Hokulea, a replica of an ancient Polynesian canoe, has sailed worldwide using these ancient techniques, proving their enduring power. Young navigators still train under masters, learning to trust the wind and waves as their ancestors did. In an age of satellites and GPS, their legacy reminds us that the greatest technology isn't always hardware. Sometimes it's the human mind, honed by generations to converse with the sea and stars. And that conversation continues, whispering across the Pacific like the crest of a wave under a sky full of guiding lights. Deep in the caves of Dunhuang, an ancient parchment hides a secret that would rewrite the history of astronomy. The oldest surviving complete star atlas in the world, painted over 1,300 years ago during the Tang Dynasty. This remarkable document, known as the Dunhuang Star Atlas, doesn't just depict constellations, it charts over 1,300 stars with pinpoint accuracy, grouping them into 283 asterisms that guided emperors, farmers, and navigators alike. What makes it extraordinary isn't just its age, but its precision. The stars' positions match modern calculations so closely that scholars suspect the Chinese used advanced observational tools lost to time. But this atlas was just one thread in a far grander tapestry of celestial knowledge. Chinese astronomers kept meticulous records of guest stars, sudden bright spots we now recognize as supernova. Their description of the explosion in 1054 CE, visible for 23 days in daylight, corresponds exactly to the Crab Nebula we observe today. Unlike European chroniclers who often dismissed such events as omens, the Chinese quantified them, noting their positions, durations, and even color changes with scientific rigor. These weren't just observations, they were data points in humanity's first long-term study of stellar phenomena. Their comet records are even more astonishing. A bamboo slip from the Han Dynasty, dating to 268 BC, documents Halley's Comet with such detail that modern astrophysicists use it to calculate changes in the comet's orbit over millennia. Other texts describe comets' tails always pointing away from the sun, a realization Europeans wouldn't grasp for another 1,500 years. The Chinese didn't just watch the sky, they decoded its patterns with a systematic approach that feels strikingly modern. At the heart of this tradition was the Imperial Observatory, where scholars like Zhang Heng invented the world's first seismoscope and armillary spheres to track planetary motions. His water-powered celestial globe, built in 132 CE, mechanically replicated the star's movements, a working planetarium centuries before such devices appeared in the West. Meanwhile, rural communities relied on star almanacs like the Zia calendar, which aligned planting cycles with the lunar mansions, 28 constellations marking the moon's monthly path. What's often overlooked is how deeply astronomy shaped Chinese philosophy. The concept of the mandate of heaven tied political legitimacy to celestial harmony, with emperors consulting astrologers to maintain cosmic balance. The sky was a mirror of earthly order, its regularity affirming Confucian ideals of stability. Yet this wasn't mere superstition, it drove innovation. When a 13th-century observatory in Gaocheng needed perfect alignment, engineers dug a trench 6 miles long to establish true north, achieving accuracy rivaling modern theodolites. The Dunhuang Atlas and its legacy challenge our assumptions about ancient science. Here was a civilization that mapped the heavens not for navigation or mythology, but as part of a unified worldview blending observation, statecraft, and ethics. Their star charts weren't static pictures, they were living documents, updated across dynasties as new discoveries refined humanity's place in the cosmos. And perhaps that's their greatest lesson. That true understanding of the stars requires not just keen eyes, but the patience to watch, record, and learn across generations. A wisdom etched in ink and silk, waiting centuries for us to rediscover. In the scorching cliffs of Mali's Bandiagara escarpment, the Dogon people have preserved celestial knowledge that defies easy explanation. For generations, their oral traditions described Sirius, the brightest star in our sky, as part of a triple star system, with one companion so dense and small they called it Potolo, the smallest seed. Here's the staggering part. Modern astronomy confirmed Sirius does have a white dwarf companion, Sirius B, invisible without telescopes. Its existence wasn't proven until 1862, yet Dogon elders spoke of its 50-year orbit and incredible density centuries earlier. How the controversy erupted when anthropologists Marcel Grioul and Germain Dieterlen documented Dogon cosmology in the 1930s and 40s. According to their accounts, Dogon priests knew details about Sirius B that seemed impossible without advanced instruments: its elliptical orbit, its heavy composition, even its rotational period. Some researchers argue this points to ancient contact with a technologically advanced civilization, perhaps even extraterrestrial visitors, as fringe theories suggest. Others propose a more grounded explanation. The Dogon might have interacted with European missionaries or astronomers who shared this knowledge before it was formally recorded. After all, Sirius B's existence was theorized as early as 1844, but the plot thickens. Skeptics note that Grioul's fieldwork methods have been questioned. Some suggest leading questions might have shaped the elders' responses. Additionally, similar Sirius lore appears in other African cultures, hinting at a broader regional tradition rather than isolated insight. Yet even if some details were influenced by outsiders, the depth of the Dogon's astronomical metaphors is hard to dismiss. Their creation myths describe Sirius B's orbit with poetic precision, comparing it to the spiral of a dancing granary, a metaphor eerily reminiscent of orbital mechanics. What's often overlooked is the Dogon's own explanation. They credit their knowledge to the Namo, amphibious beings who descended from the sky in a vessel filled with water and gave them cosmic wisdom. While this sounds like mythology, it mirrors flood narratives and star god traditions found worldwide, from Sumerian Ons to Polynesian navigators' shark gods. Could these stories encode forgotten encounters, or are they purely symbolic? The truth likely lies between extremes. The Dogon's sophisticated sky lore undoubtedly reflects generations of careful observation. Their lunar calendar, for instance, is more accurate than the Gregorian system for tracking agricultural cycles. Whether their serious knowledge came from ancient stargazers, cross-cultural exchange, or a blend of both, it challenges our assumptions about how wisdom travels and endures. Their stories remind us that the line between myth and science might be thinner than we think, and that the stars have always been humanity's first teachers. Hipparchus of ancient Greece often gets the credit for discovering Earth's slow wobble, the precession of the equinoxes around 129 BCE. But scattered across older texts and monuments, there are clues that suggest civilizations long before him might have grasped this celestial phenomenon. The wobble, which shifts the position of the stars over a 26,000-year cycle, subtly alters the backdrop of the night sky over generations. To spot it without telescopes or precise instruments would require patience spanning centuries, yet evidence hints that several cultures not only noticed it but wove it into their myths and calendars. Take the ancient Egyptians, for instance. The pyramid texts carved over 4,000 years ago speak of the imperishable stars near the North Celestial Pole, a reference to circumpolar stars that never set due to their position. But as Earth's axis wobbles, the pole star changes. Thuban, a star in Draco, was the North Star during the pyramid's construction, yet the texts also describe a time when it wasn't. Some researchers argue this indicates awareness of precession, a slow drift they might have tracked through generations of priest astronomers. Even more compelling, the alignment of certain temples shifts over millennia in sync with precessional changes, as if deliberately updated to reflect the sky's gradual turn. Then there's the Hindu concept of the Yuga cycle, described in texts like the Mahabharata, which divides time into vast epochs spanning thousands of years. The Surya Siddhanta even quantifies precession with surprising accuracy, calculating it as 54 arcseconds per year, remarkably close to the modern value of 50.29. Could this precision be coincidence, or does it point to an older, forgotten tradition of observation? The Maya, too, seem to have factored precession into their long count calendar, which resets after roughly 26,000 years. Their Dresden Codex includes corrections for celestial drift, particularly in Venus tables, suggesting they accounted for long-term sky changes. Meanwhile, Greek myths about the Great Year, a complete precessional cycle, echo Babylonian star lore, where the zodiac's shifting was linked to cosmic rebirth. What's fascinating is how these cultures interpreted the wobble. For some, it was a celestial clock marking the ages. For others, like the Norse with their tale of Yggdrasil, the world tree, it symbolized cyclical destruction and renewal. The common thread, an understanding that the heavens moved to a rhythm far grander than human lifespans, a rhythm they decoded not with technology, but with generations of unbroken observation. And that realization forces us to ask, if they could detect Earth's subtle dance without modern tools, what other cosmic truths might they have known that we're still uncovering? The story of Osiris reads like a gripping drama: murder, resurrection, and celestial destiny, but beneath its mythic surface lies a hidden astronomical code. Ancient Egyptian texts describe how Osiris, the god of rebirth, was slain by his brother Set, only to be revived by his wife Isis and ascend to the stars as the constellation we call Orion. At first glance, it's a tale of love and vengeance, but look closer and the narrative mirrors the night sky itself. Orion's death and rebirth align with the constellation's annual disappearance below the horizon and triumphant return, a celestial metaphor for the Nile's life-giving floods. The Egyptians didn't just worship the stars, they wove their movements into the very fabric of their mythology. This practice wasn't unique to Egypt. The Greek legend of Orion, the mighty hunter placed among the stars, follows a similar pattern. Ancient sources describe Orion being stung by a scorpion, the constellation Scorpius, explaining why the two never appear in the sky together, a poetic way to encode an astronomical reality. Even the Sumerian epic of Gilgamesh, one of humanity's oldest stories, ties its hero's journey to the sun's annual path through the zodiac, with each trial reflecting a seasonal shift in the heavens. These weren't just bedtime stories, they were mnemonic devices preserving cosmic knowledge in a form that could be passed down for generations. Consider the Aboriginal Australians, whose Dreamtime stories map the sky with startling precision. The emu in the sky, a dark nebula stretching across the Milky Way, appears in rock art and oral traditions that dictate when to gather emu eggs, its position signaling the breeding season. The Pleiades, known as the Seven Sisters, feature in tales across cultures from Greece to Japan to the Navajo, often linked to agricultural cycles or navigation. Such universal motifs suggest these myths weren't coincidental but deliberate, a way to anchor vital celestial knowledge in memorable narratives. The real test comes when we compare myths to historical events. The Egyptian demon star Algol, whose brightness fluctuates every 2.87 days, was associated with the evil eye of Horus, a myth that aligns perfectly with its observable dimming. Similarly, the Chinese legend of the celestial dragon swallowing the sun matches ancient records of solar eclipses, with the dragon being the moon's shadow. Even the biblical story of Joshua stopping the sun could reflect an eclipse event where the sun appeared to stand still during totality. What's striking is how these stories transcend time and geography. The Norse wolf's girl chasing the sun, the Aztec sun god Huitzilopochtli battling the stars each dawn, these aren't just colorful fables. They're observational records disguised as drama, a way for ancient cultures to document celestial phenomena without writing a single equation. And that raises a tantalizing possibility. If we listen closely to these age-old tales, we might just hear the stars whispering their secrets across the centuries. Beneath the Mediterranean waves off the coast of Antikythera, a corroded lump of bronze and gears lay hidden for 2,000 years until divers recovered it in 1901. At first glance, it seemed just another shipwreck artifact, but decades later, researchers realized they were holding the world's oldest known mechanical computer. The Antikythera Mechanism, no larger than a shoebox, contained over 30 interlocking bronze gears that could predict solar eclipses, track the 4-year Olympic cycle, and model the erratic motions of planets with astonishing accuracy. This wasn't just a calendar, it was a miniature cosmos in a box, crafted with a precision that wouldn't be matched until Swiss clocks a millennium and a half later. How did ancient Greeks engineer such a device? The mechanism's complexity is staggering. X-ray scans reveal differential gears, a technology once thought invented in the 16th century that calculated the moon's phases by compensating for its elliptical orbit. Tiny inscriptions served as an instruction manual, explaining how to read celestial positions for specific dates. One dial even tracked the timing of the ancient Olympics, proving this wasn't just a scholar's tool but a cultural touchstone. The real marvel, though, lies in its planetary displays. While most ancient cultures saw planets as wandering dots, the Antikythera Mechanism modeled their retrograde motion, the illusionary backward drift caused by Earth's orbit, using gear trains that mimicked the mathematics of Apollonius of Perga, a Greek astronomer who theorized epicycles centuries before Ptolemy. But here's the burning question: was it unique? Cicero wrote of a similar device built by Archimedes, and Babylonian eclipse records suggest the Greeks might have borrowed from even older traditions. Recent discoveries hint at a possible precursor, a fragmentary gear system found in a Mediterranean shipwreck near Crete, though too damaged to decipher. What's clear is that the Antikythera Mechanism wasn't born in isolation. It was the pinnacle of a Hellenistic scientific renaissance, where Alexandrian engineers blended Babylonian astronomy, Egyptian mathematics, and Greek mechanics. The mechanism's purpose remains debated. Some argue it was a teaching tool for philosophers, while others believe it guided naval navigation. Its eclipse predictions could recalibrate lunar calendars critical for sea travel. But its true legacy lies in what it reveals about ancient innovation. This wasn't magic or alien technology. It was the product of meticulous observation, relentless experimentation, and a culture that saw the universe as a machine to be understood. And that's the real wonder. 2 millennia before Silicon Valley, a craftsman on Rhodes or Syracuse turned the cosmos into clockwork, proving that the line between ancient and modern science is far thinner than we've ever imagined. Archaeoastronomy isn't just about studying ancient ruins. It's about stepping into the minds of those who built them, seeing the sky as they did. At Choco Canyon in New Mexico, a 1,000-year-old Puebloan complex hides celestial secrets in its very architecture. The sun dagger, a spiral petroglyph carved high on Fajoda butt, becomes a living sundial during solstices and equinoxes. As sunlight slices through slender rock crevices, it bisects the spiral precisely, a phenomenon that wouldn't work if the builders hadn't calculated the sun's shifting angles with meticulous care. But here's what's truly remarkable. This wasn't just a calendar. The same site marks the 18.6-year cycle of the lunar standstill, when the moon reaches its extreme positions in the sky. To track something so subtle over generations suggests a scientific tradition far more advanced than we've credited to these ancient cultures. Half a world away in Peru, Machu Picchu's Intihuatana stone, often called the hitching post of the sun, demonstrates another layer of celestial ingenuity. Carved from a single rock, its angles align with the sun's position during the equinoxes, casting no shadow at solar noon. But recent studies reveal even deeper complexity. The stone's irregular faces also correspond to the rising and setting points of the Pleiades, a star cluster central to Andean agriculture. When these stars vanished in April, it signaled planting season. Their return marked harvest. The Incas didn't just observe the stars, they integrated them into the rhythm of daily survival, blending astronomy with the very soil beneath their feet. Modern archaeoastronomers use tools like 3D modeling and celestial software to reverse engineer these ancient sky maps. At Scotland's Callanish Stones, researchers discovered that the monoliths frame not just the sun and moon, but also the silhouette of a distant mountain peak where the moon appears to roll along the horizon during major standstills. Similarly, Cambodia's Angkor Wat temples, once thought purely religious, now reveal alignments with the draconic cycle of lunar eclipses events tied to mythical battles between serpent deities and gods. These findings blur the line between science and spirituality, showing how ancient cultures wove celestial patterns into their worldview, yet the field faces fascinating challenges. At Ohio's Great Serpent Mound, debates rage over whether its coils align with solstice sunsets or the constellation Draco, or both. Some researchers argue that without written records, we risk projecting modern interpretations onto symbolic designs. Others counter that the repetition of certain alignments across cultures, like solstice markers in both Egypt and Mesoamerica, points to universal human recognition of celestial order. The truth likely lies in between, a mix of deliberate observation and cultural meaning, where the sky served as both clock and canvas. What emerges from these global investigations isn't just a collection of clever alignment, it's a portrait of humanity's enduring dialogue with the cosmos. From Navajo star ceilings that map the Milky Way to Polynesian navigators chanting star paths across the Pacific, these traditions remind us that astronomy wasn't invented in observatories. It was born in the quiet patience of generations who looked up, saw patterns, and dared to build their world in harmony with the infinite. And perhaps that's archaeoastronomy's greatest gift, not just decoding the past, but rekindling our own wonder at the night sky's timeless stories. The flames that consumed the Library of Alexandria didn't just burn scrolls, they may have erased entire chapters of humanity's cosmic understanding. Founded in the 3rd century BCE, this legendary institution housed an estimated 500,000 documents, from Greek treatises to Egyptian star charts to Babylonian eclipse records. Among its lost treasures, the works of Aristarchus of Samos, who proposed a heliocentric solar system 18 centuries before Copernicus, and Hipparchus's star catalogue, which mapped over 1,000 stars with coordinates so precise they rival modern measurements. But the real tragedy isn't just what we know was destroyed, it's the countless texts we'll never know existed. Their titles and authors vanished like smoke. Consider the fate of the Pinax, the library's master catalogue. This ancient equivalent of a search engine listed every scroll by author, subject, and even a quality rating, proof of a systematized knowledge network unmatched until the internet. Among its entries were maritime logs from Phoenician sailors documenting celestial navigation techniques, Persian astronomical tables predicting planetary conjunctions, and possibly even early Indian texts like the Surya Siddhanta, which calculated planetary orbits with eerie accuracy. The library wasn't just a repository, it was a global hub where Egyptian priests, Greek mathematicians, and Mesopotamian astronomers exchanged ideas across cultures. Its destruction didn't just burn books, it severed a living dialogue between civilizations. The consequences ripple through history. Without the library's resources, Ptolemy's Almagest, the cornerstone of medieval astronomy, might be a fraction of its original depth. Scholars speculate that his star catalogue, long thought original, was actually a condensed version of Hipparchus's lost work. Even the Antikythera Mechanism's design suggests it drew from Alexandrian engineering manuals now gone forever. Some historians argue this knowledge gap delayed the scientific revolution by centuries. Imagine if Galileo had accessed Aristarchus's heliocentric proofs instead of reinventing them. How differently might our cosmic world have evolved? Yet the mystery deepens when we ask, was Alexandria truly the only casualty? Across the ancient world, from the imperial libraries of Han China to the Mayas' painted codices, countless repositories met similar fates. The Mayas' Dresden Codex, one of just 4 surviving bark paper books, hints at a vast astronomical tradition mostly reduced to ashes by Spanish missionaries. Even the House of Wisdom in Baghdad, which preserved and expanded upon Greek science during Europe's Dark Ages, was obliterated by the Mongols in 1258. Each loss wasn't just a setback, it was a fracture in humanity's collective memory. What might these texts have contained? The Roman architect Vitruvius mentions a lost work by Archimedes describing a mechanical planetarium more advanced than the Antikythera device. Babylonian clay tablets reference an astronomical procedure text for calculating Jupiter's position that mathematicians only recently rediscovered using 21st-century algorithms. And then there's the legend of the Emerald Tablet, a cryptic hermetic text rumored to hold ancient secrets of celestial harmony. While some dismiss these as myths, their persistence suggests a haunting truth, that our ancestors may have grasped concepts we're still struggling to relearn. The fire at Alexandria wasn't an isolated event. It was a symbol of how fragile knowledge can be. Yet in the charred fragments that survived, like the charred Herculaneum scrolls now being read with X-rays, we catch glimpses of what once was. These remnants whisper that the ancient world's astronomical prowess might have been far richer than we ever imagined. And that realization forces us to wonder, how much of our modern discoveries are actually rediscoveries, echoes of a science that flickered brightly once before the darkness fell. The Babylonians didn't just fear eclipses, they mastered them. Clay tablets from 2,500 years ago reveal something extraordinary. The Babylonians could predict lunar eclipses down to the hour using nothing but patterns scratched into wet clay. Their secret, the Saros cycle, a repeating 18-year, 11-day rhythm where eclipses recur in nearly identical sequences. By tracking this cycle across generations, they built a database of celestial events so reliable it still holds up today. One tablet, known as the Goal Year text, even corrects for tiny discrepancies by factoring in the moon's subtle orbital quirks, a refinement that wouldn't be matched in Europe for centuries. This wasn't astrology or guesswork. It was mathematics in its purest form, a testament to patience sharper than any telescope. Meanwhile, in ancient China, eclipse prediction was a matter of imperial survival. Emperors claimed the mandate of heaven, and a missed eclipse could shatter that illusion. Court astronomers, working under threat of execution, refined their methods to chilling precision. The Book of Documents records a solar eclipse from over 4,000 years ago, while oracle bones from the Shang dynasty show eclipse forecasts etched alongside questions to ancestors. But their real breakthrough came with the Shi, a gnomon or sundial that measured the sun's shadow to track celestial motions. By the Han dynasty, astronomers like Zhang Heng built armillary spheres that modeled planetary paths, allowing them to anticipate eclipses by mapping the moon's intersection with the sun's ecliptic plane. What's staggering is how these cultures converged on similar solutions despite oceans between them. The Maya, for instance, didn't just predict eclipses, they weaponized them. Dresden Codex pages depict priests using eclipse tables to stage dramatic sky battles, where the vanishing sun became a tool of political theater. Their calculations, based on painstaking Venus observations, were so precise that modern astronomers found their eclipse records off by mere minutes over spans of centuries. Even the Greeks, who initially dismissed Babylonian number magic, later adopted their methods. Claudius Ptolemy's eclipse predictions in the Almagest leaned heavily on Mesopotamian data, proving that good science transcends borders. Yet the real marvel lies in their tools, or lack thereof. Without lenses or clocks, the Babylonians used water-filled cylinders to time eclipses, while Chinese observers noted how animal behavior shifted in the eerie pre-eclipse silence. The Polynesians, who saw eclipses as the sun being swallowed by a celestial shark, tracked them through oral chants that preserved cyclic patterns across generations. These weren't crude methods, they were tailored to their world, blending observation, intuition, and sheer ingenuity. The legacy of these predictions still echoes. When NASA Jet Propulsion Laboratory verified ancient eclipse records, they found Babylonian timings accurate to within 4 hours, astonishing for naked eye astronomy. Modern eclipse maps still rely on the Saros cycle, a direct gift from those clay tablet astronomers, and perhaps that's the deepest lesson, that eclipses weren't just celestial events to these cultures. They were puzzles to solve, clocks to set, and stories to tell, proof that the sky's mysteries belong to anyone brave enough to look up and count. The zodiac we recognize today, those 12 familiar constellations lining the sun's path, wasn't born from whimsy, but from the meticulous observations of Babylonian astronomers over 2,500 years ago. Carved into clay tablets under the vast Mesopotamian sky, their earliest zodiacal divisions were practical tools, not mystical symbols. They split the ecliptic, the sun's apparent yearly path, into 12 equal 30-degree segments, each named after the constellation occupying that space. But here's the twist: these divisions weren't arbitrary. They aligned with the agricultural calendar, marking the flooding of the Tigris and Euphrates or the ripening of barley. The stars weren't just decorations, they were a celestial clockwork guiding survival. Yet the Babylonians didn't work in isolation. Their zodiac borrowed from even older traditions. The Sumerians, centuries earlier, had grouped stars into constellations like the heavenly bull, Taurus, and the great twins, Gemini, linking them to seasonal changes. A shattered tablet from the library of Ashurbanipal hints at a precursor zodiac with 15 or 16 signs, later streamlined by Babylonian scholars for mathematical convenience. This refinement wasn't just about counting stars. It reflected a growing understanding of celestial mechanics. By the 7th century BCE, the Mul, pinned tablets catalogued rising and setting dates for zodiacal constellations with the precision of an almanac, proving these patterns were tools for timekeeping long before they became astrological fodder. The real surprise lies in how the zodiac's purpose split as it traveled. When the Greeks adopted it in the 4th century BCE, they kept the Babylonian structure but infused it with mythology, tying each sign to heroic tales. Aries became the golden ram of Jason's quest, while Scorpio morphed into the creature sent to slay Orion. This cultural layering transformed the zodiac from a farmer's almanac into a narrative tapestry. But the Greeks also advanced its scientific use. Hipparchus, comparing his star charts to Babylonian records, noticed the signs had drifted due to Earth's wobble, the precession of the equinoxes. Suddenly, the zodiac wasn't just a map, it was proof the heavens themselves were in motion. Meanwhile, in ancient India, the zodiac took a different turn. The Surya Siddhanta preserved the 12-sign system but recalibrated it to sidereal astrology, anchoring signs to fixed stars rather than the shifting equinoxes. This subtle difference sparked debates still alive today. Should zodiac signs follow the tropical system aligned with seasons or the sidereal aligned with constellations? The Babylonians' original framework had birthed two competing schools of thought, a duality reflecting humanity's struggle to reconcile celestial patterns with earthly experience. The zodiac's journey didn't stop there. Persian astronomers refined its mathematics, Arab scholars preserved it through Europe's dark ages, and Renaissance artists like Dürer immortalized its symbols in art. Yet beneath these layers, the original Babylonian genius endures. Modern astronomers still use the ecliptic coordinate system descended from those clay tablets, and the very word zodiac comes from the Greek zodiakos kyklos, meaning circle of animals, a nod to its Mesopotamian roots. What began as a farmer's calendar now spans science and superstition, a testament to humanity's enduring desire to find meaning in the stars. But perhaps the zodiac's greatest lesson is this: whether as a tool for planting crops or a mirror for the soul, it reminds us that the night sky has always been a canvas, one where cultures across time have painted their questions, hopes, and dreams. And in that shared gaze upward, we're still connected to those ancient astronomers who first dared to chart the light. From the sprawling Nazca lines etched into Peru's desert to the ancient passage tomb of Newgrange in Ireland, one thread connects civilizations separated by continents and millennia, an unshakable drive to build in harmony with the heavens. These weren't random acts of reverence. The Nazca's colossal geoglyphs, some stretching over 600 feet, align with solstice sunrises and the cyclical appearance of constellations like Orion, turning the desert into a celestial chalkboard. Meanwhile, Newgrange's stone passage, older than the pyramids, floods with golden light for just 17 minutes at winter solstice dawn, a feat requiring precise astronomical knowledge encoded in 5,000-year-old architecture. How do we explain this global phenomenon? Was it chance, a shared human instinct, or evidence of something more profound, a lost science of the stars? The most straightforward answer lies in necessity. For agricultural societies, the sky was the ultimate calendar. The Inca's sacred city of Machu Picchu, perched high in the Andes, wasn't just a royal retreat. Its Intihuatana stone functioned as a solar clock, marking equinoxes when the sun cast no shadow, signaling critical planting and harvest times. Similarly, the ancestral pueblones of Choco Canyon carved spiral petroglyphs that transformed into solstice markers when struck by daggers of light. These alignments weren't mystical, they were survival tools, turning celestial patterns into lifelines for communities dependent on the land. Yet some alignments defy practical explanation. Consider the pyramids of Giza, positioned not just to true north but mirroring Orion's belt with uncanny precision, a pattern echoed in China's Zion pyramids and Mexico's Teotihuacan. The odds of such similarities arising independently seem vanishingly small. Could there have been cross-cultural exchange? Theories abound, from Bronze Age sea travelers sharing knowledge to a hypothetical mother culture seeding ideas across the globe. But the lack of concrete evidence leaves us with a tantalizing alternative, that these cultures, through patient observation, independently unlocked the same cosmic truths. Perhaps the deepest clue lies in humanity's shared psychology. Carl Jung's concept of archetypes, universal symbols embedded in our collective unconscious, might explain why so many cultures linked pyramids with celestial ascent or serpents with cosmic cycles. The sky, after all, is the one landscape every human community has witnessed. Its rhythms, the sun's daily rebirth, the moon's phases, the predictable dance of planets offered a universal language, a template for order in an unpredictable world. When the builders of Stonehenge hauled 80-ton bluestones from Wales to frame the solstice sun, or when the Maya stacked temples to capture Venus's descent, they weren't just tracking time. They were asserting humanity's place in the cosmos, weaving earthly structures into the fabric of the universe itself. Modern technology reveals even subtler layers to this ancient dialogue. LiDAR scans of Cambodia's Angkor Wat show its temples aligned not just to solstices, but to the draconic cycle of lunar eclipses, events tied to the serpentine Naga of Khmer mythology. In Egypt, the star shafts of the Great Pyramid, once dismissed as vents, now prove to target Sirius and Orion at key dates, suggesting the pyramid was a stone embodiment of the sky. These discoveries blur the line between science and spirituality, revealing cultures that saw no divide between measuring the heavens and worshipping them. The answer, then, may lie in synthesis. These alignments weren't just practical calendars, random mimicry, or blind faith. They were all three at once. The sky grounded myth in mathematics, turning stories into star charts and temples into telescopes. Whether through shared knowledge, parallel discovery, or some deeper instinct, these ancient architects grasped a truth we're still unpacking, that the cosmos isn't just above us, it's within us, coded into our myths, our structures, and perhaps even our minds. And that realization invites us to look anew at these ancient sites, not as relics of superstition, but as monuments to humanity's first, and perhaps most profound scientific revolution. Before the written word, the night sky lived in stories passed down through generations in rhythms as precise as the celestial cycles they described. Indigenous Australians, for instance, encoded astronomical knowledge in songlines, intricate oral maps where melodies trace the paths of stars and landforms in unison. A single song might describe the rising of the Pleiades, signaling the arrival of emu eggs, while another recounts Orion's belt as three hunters pursuing the kangaroo constellation. These weren't just tales, they were survival manuals where every note held coordinates for navigation, seasonal shifts, and even weather patterns. The Karadjuri people of Western Australia still use songs to predict tides based on the moon's phases, knowledge preserved for over 40,000 years without a single written symbol. In the Pacific, Polynesian navigators transformed star lore into chanted poetry. The Hawaiian Cumulipo, a 2,000-line creation chant, doubles as a celestial almanac, embedding the movements of over 250 stars within its verses. Navigators memorized these chants, linking each star's position to ocean currents and bird migrations. The Maori of New Zealand went further, crafting wooden star compasses called war kokorangi, where carved notches represented anchor stars, while oral traditions warned of Te Wanau Marama, the family of the moon whose phases governed planting and fishing. Without parchment or ink, these cultures turned memory into an unbreakable chain, where every generation became living libraries of the cosmos. Rituals served as another living textbook. The Lakota Sioux sun dance ceremony, timed to the summer solstice, encoded observations of solar zeniths and the heliacal rising of Sirius. Similarly, the Hopi snake dance coincides with the rainy season, marked by the appearance of the constellation Scorpius, a pattern noted in their rock art centuries before telescopes. Even children's games played a role. Inuit elders taught youngsters to identify Sirius by threading beads into patterns mimicking the star's position relative to the three hunters of Orion's belt, turning astronomy into play. The durability of these methods is staggering. When anthropologists compared 19th-century recordings of Aboriginal star songs with modern versions, the star positions described still matched NAS, a retro-calculated sky maps. Meanwhile, Polynesian navigators using ancient chants successfully sailed from Tahiti to New Zealand in 1976 without compasses or charts, proving the precision of oral astronomy. What written records often miss is the fluidity of oral traditions. A single elder's song might adapt over centuries, subtly adjusting star positions to account for precession while retaining core knowledge. This living science challenges our assumptions about progress, suggesting that wisdom isn't lost when it's spoken, it evolves. From the Navajo's star sealings, woven into ceremonial hogans, to the Norse myths that preserved supernova sightings in epic poetry, these traditions remind us that the stars were never silent. They sang, whispered, and danced through generations long before they were ever written down. And in many places they still do. At Chichén Itzá, the ancient Maya built El Caracol, a spiraling tower that rises from the jungle like a stone telescope. Its narrow windows don't frame random views, they target Venus at its most extreme positions in the sky, while the stairway aligns with the sun during the equinoxes. This wasn't just architecture. It was a celestial calculator designed to track the movements of a planet the Maya considered a god of war. When Venus appeared as the morning star, it signaled the time for raids and ceremonies, woven into the very stones of El Caracol. The building's name, meaning the snail, hints at its function, a spiral path to the heavens where priests decoded the cosmos from its rooftop platform. Far to the north, Scotland's Callanish stones tell a different but equally profound story. Erected over 5,000 years ago, these towering monoliths form a cross-shaped pattern that mirrors the constellation Cygnus, the swan, during key lunar events. But the real magic happens every 18.6 years, when the moon skims the horizon in a rare major standstill. During these events, the stones cast elongated shadows that seem to slither like serpents, a phenomenon some researchers link to local myths of lunar dragons. Unlike the precision-cut windows of El Caracol, Callanish relies on raw, organic alignment, proving that observatories took as many forms as the cultures that built them. In Peru, the Incas crafted something even more subtle: the 12 towers of Chanquillo, stretching across a desert ridge like a stone comb. At dawn and dusk during solstices, the sun rises and sets precisely between specific towers, marking the year's turning points with unerring accuracy. What's striking is how these structures double as both practical calendars and sacred stage sets. Nearby artifacts suggest priests reenacted solar myths here, their rituals timed to the sun's dramatic entrance between the towers. This blend of science and spectacle reveals a truth about ancient observatories. They weren't just tools for observation, but theaters where the cosmos and culture collided. Then there's Ujjain in India, home to the 5th century Vedashala, one of the world's oldest surviving observatories. Its massive sundial, the Samrat Yantra, stands 3 stories tall, casting shadows that measure time down to the minute. But the site's true brilliance lies in its planetary instruments, stone hemispheres that chart the positions of Jupiter and Saturn using nothing but carefully calibrated curves. Unlike Western observatories, which often prioritized passive observation, Ujjain's designs were interactive. Astronomers likely placed water in the hemisphere's grooves, using reflections to double-check star positions, an ingenious fusion of hydraulics and optics centuries before the telescope. What unites these sites isn't just their function, but their philosophy. From the Maya's Venus-aligned tower to the Inca's solar gateways, ancient observatories refused to separate science from spirituality. At Newgrange in Ireland, the winter solstice sunrise doesn't merely illuminate a tomb, it floods the chamber in a golden cascade, a moment that must have felt like divine communion. Similarly, Egypt's Temple of Karnak aligns its axis so that the summer solstice sun pierces its innermost sanctuary, lighting statues of gods normally shrouded in darkness. These weren't cold calculations. They were conversations with the cosmos, where every alignment held layers of meaning, from agricultural cycles to the journeys of souls. Modern archaeologists are only beginning to decode these multilayered sites. LiDAR scans of Cambodia's Ko-Ker Pyramid complex reveal it was designed to mirror the Draco constellation during the 10th century, while acoustic studies at Malta's Haga Kim suggest its chambers amplified chants during equinoxes, blending sound and light into ritual. Each discovery peels back another layer, showing us that ancient observatories were never just about the stars, they were about humanity's endless quest to find meaning in the vast, glittering dark. And perhaps that's why they still captivate us today, not just as feats of engineering, but as mirrors reflecting our own timeless wonder at the night sky. Not every alignment in ancient ruins points to the stars. Sometimes a doorway is just a doorway. While the astronomical interpretations of sites like Stonehenge or the Great Pyramid captivate our imagination, a growing chorus of archaeologists and historians urge caution. They argue that attributing celestial significance to every ancient structure risks projecting modern fascination onto the past. After all, if you measure enough buildings against enough stars, some correlations are bound to emerge by chance alone. The controversy hinges on a critical question: were these alignments intentional, or are we seeing patterns where none exist? Take the case of Egypt's pyramid shaft. While some researchers insist they align with Orion and Sirius, others point out that similar shafts appear in non-royal tombs with no celestial ties. Could the famous Orion correlation be a fluke of geometry rather than a grand design? Statistical analyses reveal that with hundreds of pyramids built over centuries, a few aligning with bright stars isn't improbable, it's mathematically expected. Even the Nazca lines, often hailed as an astronomical calendar, show alignments that shift over time as erosion alters their positions, muddying the case for precise celestial intent. Then there's the issue of modern bias. Contemporary astronomers often approach ancient sites with high-tech tools and detailed sky maps, unconsciously favoring interpretations that match their own specialized knowledge. But ancient builders didn't have planetarium software or laser theodolites. Their priorities might have been practical, orienting buildings to prevailing winds, flood patterns, or even political symbolism rather than the stars. The Maya city of Tikal, for instance, aligns not just with solstices but with nearby mountain peaks that held spiritual significance. To reduce these multilayered sites to simple star charts overlooks the complexity of ancient worldviews. Skeptics also highlight the danger of selective evidence. For every convincing alignment, like Newgrange's solstice illumination, there are dozens of claimed celestial connections that crumble under scrutiny. The so-called world grid, linking global sacred sites to ley lines and stars, for example, often relies on cherry-picked data while ignoring mismatches. Even at Stonehenge, where solstice alignments are undeniable, debates rage over whether its builders truly understood the mechanics of eclipses, or simply celebrated the sun's seasonal return as part of agricultural rituals. Yet dismissing all astronomical connections would be equally short-sighted. The challenge lies in distinguishing coincidence from intentional design. One promising approach combines archaeology with ethnography, studying living cultures that still use traditional sky knowledge. The Dogon's Sirius lore, once dismissed as borrowed from Europeans, gains credibility when compared to similar traditions among neighboring tribes untouched by Western astronomy. Similarly, Polynesian navigational chants, tested in modern voyages, prove their precision wasn't luck but accumulated wisdom. These living bridges to the past suggest that some ancient feats were indeed astronomical, just not all of them. The middle ground may lie in recognizing that ancient cultures blended celestial observation with other priorities. A temple aligned to the solstice might also honor a local god or mark a trade route. The sky wasn't their only compass, but it was often part of a richer, more nuanced dialogue between Earth and cosmos. In the end, the debate itself is valuable. It keeps us questioning, testing, and refining our understanding of how our ancestors saw the stars. And perhaps that's the real lesson. The night sky has always been a mirror, reflecting not just light, but the boundless creativity of human interpretation. Modern science often wears the crown of progress, assuming each new discovery eclipses what came before. But what if our confidence blinds us to the brilliance of ancient astronomers? The more we uncover about their methods, the clearer it becomes. We may have dismissed their insights too quickly, mistaking simplicity of tools for simplicity of thought. Take the Greek astronomer Hipparchus, celebrated for discovering Earth's axial precession around 129 BCE. Yet Babylonian tablets from 400 years earlier describe the same phenomenon using different terminology, while Hindu texts like the Surya Siddhanta quantify it with startling precision. These weren't lucky guesses, they were the fruits of systematic observation, preserved in cultures Western academia long overlooked. Consider how we've historically marginalized non-European contributions. When the Antikythera Mechanism was first discovered, scholars struggled to believe ancient Greeks could engineer such complexity. The idea that Babylonians or Egyptians might have influenced its design was rarely entertained, despite mounting evidence of cross-cultural exchange. Similarly, Polynesian navigators who crossed thousands of ocean miles using star paths were labeled primitive until modern researchers proved their methods rivaled European sextants. This bias isn't just academic, it distorts our understanding of humanity's shared intellectual heritage. Even the language we use betrays these assumptions. Terms like Dark Age imply knowledge vanished between classical and Renaissance Europe, ignoring thriving astronomical traditions in Baghdad, Delhi, and Tenochtitlan. The Mayas' Venus tables, for instance, were dismissed as astrology until computer models verified their predictive accuracy. Meanwhile, indigenous star knowledge, like Aboriginal songlines encoding meteor shower cycles, was often relegated to anthropology rather than recognized as legitimate science. These oversights reveal a deeper pattern. When a culture's way of knowing diverges from laboratory-based methods, we risk categorizing it as myth rather than mathematics. The consequences extend beyond history books. Modern astronomers searching for supernova remnants rely heavily on medieval Chinese and Arabic records, yet these sources were sidelined for centuries. Archaeoastronomers rediscovering solstice alignments at sites like Choco Canyon now confront a troubling question. How much vital data was lost because earlier excavators didn't think to check for celestial correlations? The very tools we use to study the past statistical models, precision dating often rests on frameworks that once excluded non-Western voices, yet cracks in this paradigm are widening. Researchers like Clive Ruggles have demonstrated how Polynesian navigational charts encode precise stellar declinations, while projects like the Native Skywatchers Initiative revive Ojibwe and Dakota star knowledge in mainstream astronomy. The growing field of ethnoastronomy bridges these worlds, proving that primitive and advanced are poor labels for ways of understanding that simply differ. Perhaps the greatest lesson lies in humility. When a Dogon elder describes Sirius's invisible companion or a Navajo star priest recounts the celestial origins of healing rituals, we're reminded that science isn't a single path. It's a constellation of human curiosity, shining across cultures and centuries. The true blind spot isn't in ancient methods, but in our own reluctance to see them as equals. In a quiet corner of the University of Thessaloniki, a team of researchers huddle over a bronze disc etched with cryptic markings, a painstaking replica of the long-lost Hipparchus eclipse calculator. This isn't just a museum piece, it's a working key to the past, rebuilt from fragments of ancient texts and star charts. By recreating tools like this, experimental archaeologists are doing something extraordinary. They're not just studying history, they're reliving it. When they used the disk to predict a solar eclipse last year, the results were startling. The Greek method, dating back to the 2nd century BC, was accurate within minutes. The process reveals how ancient astronomers turned simple materials into precision instruments. Take the Greek dioptra, a rudimentary sighting tube mounted on a graduated disk. Modern tests show that by aligning it with specific stars and tracking lunar movements, observers could forecast eclipses months in advance. One team in Crete demonstrated this by replicating the conditions described in Ptolemy's Almagest using nothing but moonlight, a flat horizon, and patience. Their predictions matched historical eclipse records with eerie consistency, proving that technology isn't always about complexity. Sometimes it's about mastering the basics with relentless precision. But the real breakthrough isn't just in replicating tools, it's in decoding the minds behind them. When researchers tried using Babylonian, a goal-year clay tablets to track Jupiter's retrograde motion, they discovered something unexpected. The Babylonians didn't just record data, they spotted patterns invisible to the naked eye, like the planet's cyclical speed changes. By inputting their numbers into the tablet's grid system, modern astronomers realized the Babylonians were effectively running primitive algorithms, centuries before the term existed. This hands-on approach is rewriting assumptions. For decades, scholars debated whether Stonehenge's builders truly understood lunar standstills, the moon's most extreme northerly and southerly positions. Then, in 2018, archaeoastronomers used replica timber posts and laser alignments to simulate the site's original sightlines. The results showed the Aubrey holes, a ring of pits long dismissed as ceremonial, actually marked the moon's 18.6-year cycle. What seemed like ritual was, in fact, rigorous science. Perhaps the most poignant experiments involved Polynesian navigation. Using only reconstructed stick charts and memorized star chants, modern voyagers have sailed from Hawaii to Tahiti without compasses or GPS. Their success hinges on techniques once dismissed as folklore, like reading ocean swells disrupted by distant islands or spotting the faint glow of lagoons reflected on clouds. These aren't just feats of endurance, they're proof that ancient knowledge, when tested, often holds up better than we dared imagine. The lesson emerging from these experiments isn't just about the past, it's about rethinking how we define innovation. When a team in India rebuilt the Samrat Yantra, a colossal sundial in Jaipur, they discovered its 19-meter gnomon could tell time with a 2-second margin of error. That's more precise than many mechanical clocks, Similarly, Chinese researchers studying the Shi, an ancient gnomon mentioned in Confucian texts, found its shadow measurements could pinpoint the summer solstice to within hours using nothing but a stick and a flat stone. What's thrilling about this work is its humility. By stepping into the shoes of ancient astronomers squinting through reed sighting tubes, chanting constellations, or carving notches into bone, we're not just uncovering lost techniques. We're rediscovering a way of seeing the world where the sky wasn't a distant mystery, but an intimate map etched in stone, whispered in song, and written in the stars. And sometimes the best way to move forward is to first look back, with our hands as much as our eyes. The ancient stargazers didn't just study the sky, they lived it. Unlike modern astronomy, which often separates science from spirituality, these cultures wove celestial patterns into the very fabric of daily existence. For the Maya, Venus wasn't merely a planet. Its rising signaled the time to plant corn or wage war. The Egyptians didn't just chart Sirius's heliacal rise. They tied it to the Nile's life-giving floods, a divine clockwork governing survival. This wasn't superstition. It was a sophisticated recognition that the cosmos and Earth were threads in the same tapestry, each tug influencing the other. What's striking is how this perspective mirrors cutting-edge ecological thought today. Modern systems theory teaches that everything is interconnected: climate patterns, ecosystems, even human societies. The ancient Babylonians would have nodded in agreement. Their celestial omens linked planetary movements to river levels and crop yields, not as mystical portents, but as observable relationships. When Jupiter entered a certain constellation, they anticipated drought. When Mars lingered near the Moon, they prepared for unrest. These weren't random guesses. They were early attempts to model a chaotic universe, much like how modern scientists use data to predict El Niño cycles or economic shifts. The Polynesians took this further, treating the ocean and sky as a single navigational matrix. Their star paths didn't exist in isolation. They accounted for currents, bird migrations, and even bioluminescent plankton blooms. A modern ecologist might call this a whole systems approach, but for Polynesian navigators, it was simply common sense. Similarly, Aboriginal songlines fused landforms with star positions, creating living maps where geology and astronomy were inseparable. In an age of GPS and isolated specializations, their wisdom whispers a reminder: true understanding comes not from dividing the world into fragments, but from seeing how the pieces converse. This holistic vision extended to time itself. While we slice existence into seconds and fiscal quarters, ancient cultures perceived time as cyclical and layered. The Hindu concept of yugas, the Mayan long count, even the Greek great year, all described vast, repeating epochs where celestial and earthly rhythms intertwined. Modern physics now echoes this with ideas like eternal inflation or cyclical universes, but without the poetry. When an Inca priest marked the solstice at Machu Picchu, he wasn't just resetting a calendar. He was participating in a cosmic dance, ensuring the sun's return through ritual as much as observation. Yet the most poignant lesson lies in their humility. Ancient astronomers knew their knowledge was incomplete. The Maya constantly refined their Venus tables. The Babylonians updated eclipse predictions across generations. They saw science as a living dialogue with the unknown, not a final pronouncement. In an era where algorithms promise omniscience, their example is a grounding force, a call to stay curious, adaptable, and reverent before the mysteries that still glitter beyond our grasp. Perhaps that's why their legacy endures. From indigenous fire ceremonies timed to Orion's rise to farmers who still plant by the moon's phase, these ancient connections persist in quiet corners of the modern world. They remind us that the stars aren't just distant specks to be analyzed, but guides, teachers, and mirrors of our own place in the universe. And in rekindling that relationship, we might just find our way back to a science that doesn't just calculate the cosmos, but converses with it. From pyramids to star disks, the celestial legacy of ancient cultures isn't just a collection of artifacts, it's a challenge to our modern assumptions about knowledge and progress. These weren't primitive people stumbling upon cosmic patterns by chance. Their monuments, manuscripts, and myths reveal a deliberate, systematic study of the heavens, achieved without the crutch of modern technology. The Great Pyramid's alignment to true north, the Nebra Sky Disk solstice markers, the Maya's Venus tables, these weren't accidents. They were the fruits of generations of observation, calculation, and an unshakable conviction that the sky held answers. But here's what unsettles some scholars: gaps in the record. Why do Babylonian eclipse predictions outshine medieval European ones? How did the Dogon describe Sirius be centuries before telescopes? Some argue these are fragments of a larger, lost science knowledge that slipped through the cracks of war, decay, or cultural upheaval. Others suggest a simpler truth, that ancient minds were just as capable as ours, their achievements born of patience rather than secrets. After all, tracking the stars requires no advanced tools, just time, dedication, and the willingness to pass down wisdom across centuries. The real revelation isn't just what they knew, but how they knew it. Unlike modern science, which often isolates disciplines, ancient astronomy intertwined with agriculture, architecture, and spirituality. The Inca didn't just build solstice markers, they wove them into rituals that synchronized harvests with celestial events. The Polynesians didn't merely memorize star paths, they embedded them in chants that carried navigational data across generations. This wasn't science for its own sake, it was science in service of survival, a dialogue between earth and sky that modern specialization has muted. Yet for all we've decoded, some mysteries resist explanation. The Antikythera Mechanism's gearwork hints at Hellenistic engineering prowess we've barely glimpsed. The Surya Seddanta's planetary math suggests influences from lost traditions. Even Stonehenge's lunar alignments, once dismissed as folklore, now reveal a sophistication we're only beginning to measure. These aren't just puzzles, they're invitations to stay curious, to question the timeline of discovery we've taken for granted. So were they lucky, perhaps in part. But luck doesn't account for the precision of Babylonian eclipse cycles or the global echoes of celestial myths. What if their greatest advantage wasn't lost technology, but something we've undervalued: the art of long-term observation? In an age of instant data, we've forgotten how to watch the sky for decades, to let patterns emerge slowly, as they did for the builders of Newgrange or the scribes of the Dresden Codex. As we peer deeper into their world, one truth emerges: the ancient astronomers weren't so different from us. They asked the same questions, marveled at the same stars, and sought meaning in the cosmos. Their methods may seem foreign, but their legacy is a mirror reflecting not just what they saw, but what we might rediscover if we're willing to look up with the same wonder. The stars haven't changed, only our way of listening has. So what do you think? Were these ancient achievements a product of lost knowledge, or simply the untapped potential of human ingenuity? Drop your thoughts below, and if you've enjoyed this journey through time and space, don't forget to subscribe. The past has more stories to tell, and together we'll keep